please.
All right, so good afternoon, everybody. My name is Dumitru Roman, and I'm here with Mark Burgess and Nikolay Nikolov for discussion around the topics of the DataCloud project. DataCloud project is a project funded by the European Commission in the area of big data and cloud. And today we will have a discussion around the topics of the project, in particular data pipelines. We have the honor of having today here Mark Burgess, who is one of the advisory board members of the DataCloud project, and Nikolay Nikolov, who is the technical coordinator of the project. We will go through a number of questions, and we will leave the participants to express their opinions and thoughts around data processing in general in the context of cloud, specifically for data pipeline. So I will just start with one very generic aspect of data processing. So what do you think is the difference now in terms of data processing, and what is new now compared to, say, 10 years ago? And particularly how the evolution of the infrastructure when it comes to cloud, fog, and edge impacted data processing in general. So I'll give the floor to Mark to start with some thoughts, and then we will go to Nikolay. So Mark, the floor is yours.
Okay, I get to go first. All right, thank you. So 10 years ago, when was that? It was 2012, right? It's hard to imagine. 2012, I think, was well, it was an interesting time because it was a time of great innovation when people in the mainstream of computing were moving into the cloud for the first time. Perhaps the cloud was relatively new. First movers were already there, but mainstream business sort of gradually beginning to wander in. And I think there was a lot of experimentation with different technologies around that time, which is gradually being undone over time. You know, as technologies become more commoditized and more standardized, we have a way of turning innovation back into the thing that we were using before by some circuitous route. And so a lot of those sort of innovative approaches from 10 years ago that were quite experimental have been folded into sort of more mainstream approaches to processing and infrastructure, methods of management and communication, setting up machines and so on, that were being used perhaps before more on premises. So today it's we've sort of settled into more kind of habits, old habits again, which is good because it means that I think people understand things perhaps a little better and things are more standardized. But I do feel that we've lost perhaps some of the more innovative aspects of ideas that were being thought and created around the term, well, 10 years ago, 2012-ish, was a more interesting, exciting time for me in terms of infrastructure. In terms of how data processing has changed, I'm not sure it's changed too much. There is, of course, more support in terms of languages like Python for data processing in a commoditized way. There are new languages, a few new languages like Go. Go is being touted as perhaps the successor of Python in some sense. It's sort of a faster, more modern language, but quite easy to learn and quite cloud friendly. Obviously, something designed by Google, so ideal for the Google Cloud, but also it's a general purpose language. So there are a few innovations like languages and notebooks and things like this, which have become more accepted and widely used. But I think the main approaches to data processing are pretty much the same as they've always been. Scientifically interested people programming and cobbling together bits of infrastructure in a fairly haphazard way, but with a few extra tools to make it happen in the cloud.
Okay, so you haven't seen any radical change in data processing in the last 10 years, to say?
I think not. I think not. Although, correct me if I'm wrong, if you guys maybe know something that I don't know.
Great. Nikolay, do you have some thoughts on change in data processing over the years?
Yeah, in terms of data processing, maybe not so much. I'd say nowadays, as compared to 10 years ago, there are more devices which are able to do more processing. That means that you have a larger number of these connected devices with the Internet of Things, and ever more resources crammed inside of the chips, and they're getting better at compacting processing power, which is something kind of positive for, when you perform data processing, it's better to have this availability of the hardware resources. And then in terms of processing, I'd say, well, we've had virtualization for a while now. It's not something new that appeared in the last 10 years. I'd say there's some more wide use of certain virtualization technology or container technologies now rather than 10 years ago, which are very popular for this type of distributed applications. Not so much for data pipelines for now, although there are some developments there. And on the other hand, in terms of data processing, again, it comes like more data because of these number of devices growing to the point where it's just no longer practical to centralize data processing for certain applications. I think in the 2010s, we were talking about couple of billion of connected devices. Now people are saying in 5 years or 4 or 5 years, horizon is going to be 75 billion devices. So there's a lot more data to be processed. Otherwise, it becomes dark data, it just gets hoarded and the value is lost.
And Nikolay actually makes a great point there that one of the things which has been in the background over this course of evolution, as it were, is the arrival of new hardware. So GPUs have become turned from something that was a specialized chip for graphical processing into a matrix processing engine for more general kind of processing. And these specialized chips that are being designed as well, FPGA designs, etc. And one of the interesting things that's happening now, I think, is the arrival of RAM as a service. Of course, one of the big problems in data processing is how to store data and represent it, keep it in one place. Can you connect enough memory to a single unit to be able to process it, or do you have to distribute it across multiple systems? And we went from these mainframe systems in the 70s, 80s, 90s, where you could sort of plug in extra boards and activate them on demand, from one kind of that sort of locked-in architecture to this commoditized architecture in the cloud, where everything was built of off-the-shelf PCs, where you couldn't really plug in new stuff without sort of rewiring the data center. But now that that is starting to change as well, and there's the arrival of services like plug-in RAM as a service. So you can now use these highly efficient switching technologies, whether it's fast Ethernet or InfiniBand or whatever, to connect RAM servers to your PCs, so that you can essentially give every computer an infinite amount of RAM and reallocate that in software. So this kind of software-defined infrastructure is extremely important in terms of how we go about optimizing the processing of data, even though the sort of programmatic, algorithmic approaches are pretty much the same.
So it's more hardware serviced in the cloud, plus more data that you see. Now, let me ask you, like, in this change of ecosystem, to say it so, do you foresee any kind of radical technologies, or do you see more like incremental steps in when it comes to data processing? Or do we need some to do things very differently than we have done in the past because of this more heterogeneity of hardware, more more data?
I think that the heterogeneity is the big issue here. Not only because scale introduces a wider range of devices and sources of data, different data formats, and so on, but also that what we really have today in terms of software is a mishmash of different technologies that have been cobbled together. Nobody's designed the cloud, right? It's like a marketplace where people come with their goods and they try to stick them together into new things. And it's a gigantic curry of different components. It doesn't always smell too good. But the technologies we're using today to put together data into pipelines, for instance, to take a source of data somewhere, to share it with a particular kind of processor, perhaps to transform it from one data format into another, to put it into a certain algorithm, to massage it, to filter it, to apply, put it into a neural network or something like this. There are many stages in these processes which lead to these data pipelines, but the technologies for doing that are also extremely immature and often written in less than optimal programming languages. They're quite slow, and there's a lot of individual work that's needed to fit the pieces together. It's not like nice Lego bricks or breadboarding circuitry like you have in electronics, where you can design a circuit, stick it together, and you can test it and make it work. And then you can print the circuit board, mass produce it and make it really nice and efficient. It's still very much people plugging things together, trying to make connections and hoping for the best. There are lots of bugs in the software. It's quite unreliable. And of course, the network itself, the internet itself, is a very inhomogeneous entity with parts that are very slow and places where it's very fast. And this also creates a lot of difficulties. Today, I think the technology is still remarkably centralized. When cloud was invented, it was invented by these giant companies, AWS, Google. They put the cloud into their huge data centers to have efficiencies of scale. And that means that most of the data processing is taken from the edge and transported across the network into these centralized places to be processed and perhaps moved back again, which is quite a slow and inefficient process. The promise of the new era, especially all the stories about 5G and the new telco technologies, which emphasize the role of edge computing. There, a lot of the design of 5G, which is still not realized, is that you put a lot of that data processing at the edge so that you don't have to transport data. You move the processing to the data instead of moving the data to the processing, because it's cheaper to do that, it turns out. And we're still very, very early days for that. And the technologies for doing it, I think, are very slowly being developed, but they're hardly adopted by a wide variety of people. And the software certainly doesn't match the hardware at this point. So there's still a long way to go on that score.
So Mark, you touched upon a keyword that I think is very relevant in this context, which is data pipelines. It's a very broad concept. So would like to ask both of you, how would you define this concept of data pipeline in connection to the general area of data processing? And What aspects do you consider relevant when we talk about data pipelines?
Yeah, so I would kind of look into more like big data pipelines, which I think are more interesting. Or I mean, data pipelines would be, composite pipelines, so that they're composed of different stages or steps or pipes for processing data. And nowadays, with big data, that would be data with the V's of big data, the so-called V's of big data, which would be this volume, velocity, variety, validity, etc. These. So these are they require this management of the resources and the management of the data. So that's what I look at when it comes to pipelines, these aspects.
We're in this pipelines are a curious kind of thing somewhere between real-time processing and batch processing, right? In the world of data processing, in the olden days, should we say, like 80s, 90s, data processing was a batch-oriented thing. You would collect a bunch of data, download from your satellite, hundreds of tapes, you'd upload them somewhere, and you would process them by a batch job, which would run for hours or days, and out would pop the result, and you would maybe feed it into the next stage. With the arrival of the internet and cloud and so on, you have the possibility of being able to move data through a series of transformations in smaller batches, or you could almost say real time, more like a packet network. So you could imagine sending one small batch, having it processed, passing it on to the next stage, doing it again, and so on. Sometimes that works, sometimes it doesn't, because sometimes you need a certain amount of data before you can do anything with it. So you may have to collect, say, 12.5 terabytes before you can run the first computation, or whatever it is. So there are a lot of interesting constraints with data pipelines, which are both hardware and software problems. The hardware problem is obviously in terms of the speed and the processing, the serialization or the parallelization of computation. The software problem is how do you aggregate the data enough in a single location to be able to apply the algorithm? Do you have a method to do the computation in a certain way? And then, of course, there are different kinds of stage. So for some people, pipelines are what they call ETL, which is basically loading data into a processor from a source. You're just uploading it into a database. That's one stage of a process. But then there are also things like computing results based on those data. So taking a graph and finding its busy points or its hotspots or whatever it is, filtering data, enhancing images and so on. And no matter what your algorithm is, whether it's a neural network or just some linear algebra, whatever it is, the stages are very dependent on the capabilities of the hardware and the software at a particular location. And how much you can do in one stage depends very much on how the software has been designed. So this sort of gets in the way of commoditizing data processing, because there are very few tasks or transformations that can be commoditized in a way that anybody can just pick it up and say, okay, I need to apply that thing to my data. Compare that to, say, electronics, where you have electric circuits and wires and standard components like resistors, capacitors, diodes, transistors, and switches and things, amplifiers, and even these composite things like amplifiers and flip-flops and switches and logic and all of this. You don't really have the analog of that in software systems, because data formats are different, so the inputs are different. It's not a simple current. Accuracy may be different. Is it 32-bit? Is it 64-bit? is it, least significant byte first, or the other way around? Is it text-based? There are so many details in the representations of software that make it almost next to impossible to commoditize these things in a simple way. And I think that makes it very challenging to make simple plug-together circuitry for software-defined data processing compared to the way we've made circuitry for electronics in the past. But that is the challenge, I think, for the future.
Yeah, absolutely agree. I think what you touch upon, this requirement for knowledge, like if we talk about electronics, you receive, some formal training in electronics, and then you can build circuits. And nowadays with data processing, it's you need formal knowledge in specific technical spaces like Spark technical space, or like Google processing or Amazon processing, and then you need very, very deep knowledge in a certain technical stack, which is not readily available. So making this kind of widely available, so that if you have an IT, let's say, a team, you can set something up. It's actually, I think, the biggest challenge we face now.
This brings me to the next topic on stakeholders for data pipelines. So we know that depending on the abstraction level we look at pipelines, we can have data providers, consumers, maybe the more like domain experts or business experts, maybe more data scientists, data ops. What's your view on the ecosystem for data pipelines? Do we need something like that? Who would be the key stakeholders, and how should we make it easier for all these stakeholders to complement each other to manage data pipelines?
I think this is a very hard problem, because if you want to create a system which is commoditized, a general, for general purpose use, you need to get everyone to agree on something, like create a standard. We've had standards bodies in the past. You have IEEE and all these different bodies that standardize things, but these are committee-driven organizations, often run by the major corporations, like the telcos and the network technologists and so on. So they have vested interests in pushing certain technologies and standardizing in certain ways. But the kinds of technologies that are being standardized at the moment are around open source, where more people could used to be able to play a role in the development of ideas and software. Or increasingly, open source technologies are also being taken over by these large players, especially Google and Facebook, to mention a couple. And I think it's going to be very challenging to find a set of primitive technologies that can be plugged together in a simple way that will enable a wide range of stakeholders to have their interests represented. Back in, actually 10 years ago, interestingly enough, I came up with this idea while working with Cisco, which I call workspaces, where the idea was that you would be able to create this kind of circuitry, right? You could just take a data source and say, I want to connect it to that thing over there. Pretty much like you have in electric circuits, or in music, you have MIDI, to connect devices together, and it's a signaling protocol. You can imagine having a kind of data sharing protocol where people could exchange data in a straightforward way without too many constraints or technical requirements. And this could be standardized across a number of different languages and so on, and made easy for people to plug things together. We don't have anything like that at the moment because, as Nikolay said, you need specific technical knowledge of the software, and these things are so complex that you often need to spend 6 months, learning how to connect two containers together with a service mesh or something like this. You need to study these technologies, and they're very complex, difficult beasts. They're still quite buggy. And trying to build up a system around this requires a lot of investment in development as well as having the tools sort of readily available. And I think this is a big problem, right? So somewhere around 10 years ago was that transition where the world shifted from being something where people made their own stuff and connected it together by themselves to requiring pretty technical programmers to help them, because we switched to a kind of API view of the world where you needed developers. Developers took charge, even of the infrastructure itself. So you couldn't just connect together a few things and make something work in an afternoon. You needed to start developing software to make things happen. And the level of, the barrier to entry has become much, much higher to do even simple things. I think that is the difficulty in getting stakeholders to feel like their needs are being met. Everyone needs developers today to help them.
Absolutely. And just to add to that, well, I think what you're saying, Mark, is exactly true. And I think in DataCloud, since I put on now the DataCloud hat, and I think one of the key things, the key kind of baseline philosophies we kind of have adopted is one of empowerment of the stakeholders, and trying to come up with solutions that stakeholders are necessary throughout the life cycle stages of a big data pipeline, and try to build tools and services that are catered toward their domain of expertise, which is to say, to kind of have this separation of concerns, because you can't really build up a big data pipeline without having, a technical expert implementing the actual processing of the steps. What you can do is take advantage of the domain expertise of a domain expert and kind of build the framework of a pipeline and then fill in the technical implementation separately. So this type of, separation of concerns where could enable more stakeholders to be involved in a big data pipeline development.
Great. So let's go a little bit maybe deeper into what would you have to do with the data pipeline? So can you maybe comment a little bit on tasks that you'd have to do with the pipeline, or phases that are, first of all, are there any such generic, is there a generic life cycle for data pipelines, or do you think it will be very case by case specific? And if there is such a generic kind of life cycle of pipelines, what are the steps or tasks in such a life cycle?
Again, it's because each case, each data set is a unique thing, it's quite hard to generalize things. Even something like loading data into a database, right? Sounds like an easy thing. But you have the data format. Is it a text file? Is it a stream coming from some thing? Is it a comma separated data file? Is it separated by tabs or spaces? Does it have to be parsed? Is it JSON? Is it XML? God forbid. We need to be able to transform data from one format into another and then load it into a data model inside a database, typically for some caching purposes to make it addressable. And then you have issues like, do you need random access capability on the data? Do you need to look up things through indexing? Or do you need to read it sequentially because the order is important? Is it a graph or a relational structure? What kind of database and what kind of database query language, technology, etc., are you going to use to make this to put the data in and take the data out again. So there's the source, and then there's the consumer from this sort of intermediate cache, which is a database of some type. And each of those conversations is a unique experience depending on the requirements of the process itself. So as you can imagine, having some kind of generic tools for converting comma-separated files into JSON or something like this, you have to make, even then, a whole bunch of assumptions about how it's going to take place. You need to name the fields. You need to add semantics. What do these numbers mean? This is all, actually, I mean, going back to the original question, what's changed in the last 10 years? We maybe missed a step there because, for 10 years ago, data were pretty much comma-separated files or something like this. And the fields weren't labeled. You knew pretty much what the fields were because you collected the data yourself. You didn't bother to document it because you wrote all the software yourself. You did everything yourself. But now when you're involving many different parties, labeling the data and marking or defining the semantics of what you should do with the different bits of data, what you're allowed to do, what it makes sense to do, and what they actually can be interpreted to mean. That is an extremely difficult problem because not everybody will necessarily agree on that. And you may transmit a data value with one interpretation and somebody will receive it and imagine it to be something else, which is a source of semantic error, not just numerical error or parsing error or something like this, but actually interpretation error. And this is becoming worse or exacerbated, amplified by data pipelines when they have to pass through multiple actors and multiple stakeholders, I think. And the risk of making mistakes and the possible ways of making mistakes is becoming even richer and more exciting. It's quite exciting. So I think this is an enormous undertaking to try to make sense of all of this world of rich data, what we're going to do with it, how we're going to deal with it, how we can try to standardize certain aspects of it. Are we going to use it for batch processing? Are we going to turn it into a service? Reading and writing. Is a database considered just a cache or is it an archive? What is the role of time in this? Is a data set tied to a specific moment, a specific location, space, or time? Or is it representing something generic that can last for eternity? Mm. These are enormous questions that are barely beginning, we're barely scratching the surface of these issues.
Yeah, to add to that, so you describe a complex picture, which is absolutely correct in my opinion. Well, if you think about the pipeline, then when you run the pipeline, you need to deploy it on a set of resources. And for that, you need to calculate like how much resources do I need for the different stages of my pipeline. So I'd say if we talk about life cycle of pipelines, we should consider also this process of calculating the resource or scheduling the resources, enacting the actual deployment of the pipeline. That's another complex issue because you're dealing with heterogeneous resources which are available, as you mentioned before, Mark, over different networks and different quality networks, different speed networks. Maybe at runtime, there are some adaptations that need to be performed to the deployment so that, devices go online, offline all the time. So if we're talking about some kind of streaming, a data flow kind of pipeline where the data are continuously going, then you might want to have some adaptation at runtime as well. And going one step before that, there's been since a while now, I think early 2000s, maybe around 2000. Yeah, I don't remember the exact year, but when people started talking about process mining and in the context of data workflows and business processes, where you need to discover based on like in complex enterprise based pipelines. You don't really have a formal definition of a pipeline, and you need to discover it in order to formally define it as one, and to control it using a business process management system or a workflow system. So there is also this process of discovery based on whatever you have available in your event logs and databases.
So we have seen a lot of interest in data analytics, AI-driven data analytics with machine learning, deep learning, and so on. What do you think the roles of data pipelines in this context are? Are they necessary for supporting machine learning-driven analytics tasks, or can you do easily machine learning without having to wonder about management of data pipelines?
I suppose it depends what you mean by data pipeline. For me, in a way, it's data pipelines all the way down. It's really not turtles. The turtles are all data pipelines. Even, every database query is a pipeline that that begins perhaps with a question, but it gets turned into a number of threads collecting data, which are then joined and integrated from multiple parallel searches. Whether it's in software or in hardware, it's circuitry, right? It's basically circuitry. And when circuitry comes together to a single outcome, we call it a pipeline in some sense. So I think no matter how we phrase it, no matter how we frame the problem, there are data, whatever we end up calling them, there are data pipelines, and there are going to be data pipelines on every level of technology now and in the future. From the CPU, where pipelines make CPU instructions more efficient, to wide area networks where data are being collected from multiple sources and integrated, and then being spread out, duplicated for redundancy, for data security, and so on. Data pipelines are the major challenge of the internet. In a way, you could say it's the 8th OC layer of the networking model, right? I mean, you start with this communications, packet switching, TCP/IP, service-driven things, and then what are you going to build on top of that? Well, you're going to build handshaking for data semantics. It's not just packets, it's what kind of packets. What do the packets mean? If I offer you X, can you accept X, or can you only accept Y? So this ability to handshake data and data semantics is a huge unsolved problem, and it's data pipelines all the way down.
Yeah, I think you're absolutely correct. And data pipelines, even if you want to take an let's say a data scientist view and say, okay, data pipelines are about my pre-processing of data, and I do analytics. It's still, unfortunately for data scientists, it's still going to be the majority of the time that they spend on analytics tasks. It will be for data preparation, and that involves this type of content negotiation, data pre-processing, and it's absolutely necessary to have data pipelines.
Another topic which is a bit more sensitive when it comes to data, it's security, privacy, and compliance. How do you see these aspects being reflected in data pipelines in general? And where do you think we are with supporting security, privacy, compliance requirements when designing, deploying, running a pipeline, data pipeline?
Honestly, I have no idea what goes on inside people's private homes. I think we might be terrified if we actually knew the details of what goes on. every day we see new challenges. It's funny because I was working with a security company last year and this year, and it had been something like 15 years since I'd formally worked in computer security in the past. And I figured I'd forgotten, I don't know what's new, right? So I asked somebody on a call once, tell me what's new in data security. It's been 15 years. And he laughed at me and he said, dude, in data security, it's incremental improvements, nothing much changes in data security. And I suspect that's probably true, that the challenges of 10 years ago are the challenges of today. We haven't made much progress. And there's been a greater awareness of things like privacy, thanks to the GDPR and initiatives on a political level, basically on a political level. And then also on a political level, things like SOX compliance for financial regulations and so on, when data are of a certain sensitivity, especially financial transactions where money is involved. So we tend to only take security seriously when money is involved, or and that includes the privacy thing, because you can be sued by people for money. So putting my cynical hat on, which is, since it's Christmas, I would say that security tends to pop up when money is lost because of mistakes that are made, but mistakes are made all the time. It's the software way, we deploy and then find the bugs and then we try to fix them. There is less design awareness than there probably ought to be around these issues, because people are short on time and resources, and they don't often necessarily have the right expertise to know all the possible ways that people may attack them. So again, it's another one of these pernicious problems that won't be solved anytime soon. And we will be coming back to it in 10, 20, 30 years again in the future.
Yeah, I agree. So I don't think we're likely to come up with a holistic kind of solution to anything resembling total security. On the bright side, I'll try to add a positive kind of perspective here. I think when it comes to this type of data pipelines that involve the computing continuum, there are some low-hanging fruits. For example, this type of distributed edge processing scenarios, like a healthcare, let's say IoT scenario where you have digital health sensors deployed at the person's home, that in such scenarios, I think it's possible to have this, to deploy the stages of a data pipeline where the stages are needed. That means that no data are transmitted outside of where they need to be visible. And that's just taking advantage of this ability to decentralize the computation, as you mentioned, that to move the computation to the data rather than the other way around, which would improve the privacy and security somewhat. But I agree, it's this type of encryption on a protocol level, on application level. These are still aspects that we're using technologies from a while back, and let's say they're kind of application or pipeline specific considerations rather than something that can be holistically solved for any case, anytime.
I think you hit the nail on the head there, Nikolay, with I call it the first rule of distributed systems, that if you don't need to transport data, don't send it over the network, right? That's a good rule of thumb. And it's a rule that we've kind of violated over the last 10 years because of the centralization of cloud and because of the reliance on the network. I do remember, and it also goes to scaling, how do we scale things? This is a central theme in everything we've kind of discussed now. How do we how do we scale data, transportation? How do we scale computation? How do we scale semantics, interpretation? If you've got 20 bytes, that might mean something, but if you've got 20 terabytes, the meaning of that is totally different to the meaning of 20 bytes, right? Even if it's, the same kind of data. So all of these things require an understanding of scaling and the role of scale. And that is something that computer science has a poor track record on. I'm a physicist by training, and you can say that in physics, scaling is perhaps the central issue across much of physics. How things change as you go from one scale to another. But in computer science, we haven't begun to appreciate that yet. We think of scaling as throwing more resources at a problem, increasing the number of computers or CPUs. But we don't necessarily appreciate how that changes the interpretation or the meaning of the security or the properties of the system in important ways. And that's something we're going to have to confront.
Let's stop a little bit on use cases for data pipelines. What do you think are the most representative type of use cases for data pipelines, if anything like that exists at all? I'm thinking, I know, maybe IoT, machine learning, and maybe talk a little bit about also applications of this kind of use cases, like application domains. Which one you think will most benefit from support for data pipelines?
Nikolay, you want to go first?
Sure. In terms of high-level domains, I think Internet of Things, machine learning, artificial intelligence, those are the classic examples. And I think definitely it's always something that's required there, that you have this data processing, and this needs to happen usually in stages, and those are quite well defined. In terms of application domains, what pops out for me is examples like, so first thing I thought of when we were talking about the previous topic was digital healthcare, where you have, sensors in patients' homes. I'd say probably industry 4.0 or industrial control systems, where you have a lot of sensor data that is input to actuators and helps control a factory. I'd say there's good space in smart cities nowadays, that you have a lot of conglomeration of different things like geospatial information alongside, sensors producing data alongside all kinds of other data that can be produced by different things connected to the smart city. Marketing and retail on the internet, especially because there it's where a lot of data gets transmitted between a person's browser and some kind of server processing this data in order to find things out. So those would be the most kind of prominent examples that I can think of. And I think these kinds of domains are only extending from now on. It's going to be more because digitalization is spreading more and more throughout the industries. So as it becomes more, bigger part of control of different things that we do in life, or bigger part of how we do decision making, analytics or reporting, it's going to be even more important. So now's the time to think about data pipelines.
Great list of cases there. Let me add that for all of those edge computing, smart city things, we can generalize that to the virtual world. So, gaming, the metaverse that we are starting to hear more about now, which of course is a kind of gaming as well. The very system we're using now is Zoom. These virtual meetings are a form of data pipeline, in a sense, a very simple one. But we think of these more modern, new cases like AI and data transformations. But there's a whole bunch of traditional cases like production systems, music production, like recording music, processing it, turning it into CD, transforming the data format into something that can be streamed. That's another kind of pipeline. TV, film, any kind of business process, actually, and any kind of economic process, from a payment, card payment, from an edge device or online things, it goes through a number of processing entities. And whenever there is a collaborative network of processing entities, there will be data pipelines. We're used to thinking about the internet as being computers and switches and routers, but the financial system is also edge locations, switches and routers. The banks are the routers in the financial network. In supply chains, logistics, the routers are, of course, ports and warehouses that temporarily cache goods and services that can be put into containers and shipped around the globe. It's another kind of network where it's basically a pipeline. And we will be using, for every physical thing that happens, we are creating these digital twins or these parallel virtual systems that are tracking and monitoring them in the virtual space, because it's, of course, nice to have that intelligence, I suppose, and to do predictive analytics and things based on a model of the thing that you're physically enacting. So in all those cases, these very traditional things that we tend not to notice anymore, like just getting your food into the shops, and with all the supply chain issues that are going on at the moment, all of those things are data pipelines too.
Great. Mark, you have been working on the concept of semantic space-time. Can you say briefly what this is, why do you think it's needed, and how do you see the role of data pipelines in this context?
Semantic space-time. This comes out of research that I've been doing for, well, 20, 30 odd years now, and it was kind of a summary. So it came out of something called promise theory, which I developed, which is a theory of cooperation and interaction between things, whether humans or devices, machinery, trying to create that sort of picture of the human-machine interface on a network level. And it occurred to me that there are really two concepts behind all of the modeling that we do in data and in physical world. And that is where things are and when things happen. So there are events that occur at a certain place and a certain time. But is it a physical location? Is it a virtual location? Is it an address and an IP address, or is it a geographical coordinate? Is it a moment in time measured on the clock we have on the wall, or is it measured in terms of a sequential step in a computation? Right? The notions of space and time actually govern pretty much everything that happens both in the physical world and in the computational world. Inside a CPU, we have a stream of instructions, and each one of those instructions is a tick in a process, right? It's a clock advancing, but each time you execute a new instruction, we even call them, there's a CPU clock. So the CPU has a kind of notion of time, but then the PC as a whole has another notion of time. It has a little clock chip which keeps time. It's totally independent of the CPU time. And these other chips in the computers each have their own time. And so all these bits and pieces disagree about what time it is. And yet, when they communicate and interact, they have to synchronize. And that creates a kind of shared time. And so these notions of space and time, where and when things happen, are incredibly complex, and they are pervasive throughout the internet. And this semantic space-time model that I've worked on is really a model of that, and how to understand it on multiple scales, from the smallest CPU things to the widest areas of time across the globe, and maybe even across the solar system eventually. So it's very complex. It brings in multiple issues in terms of computation, counting, in terms of relativity. You know, even Einstein's relativity gets involved when we have satellites in passing. You know, anything to do with GPS involves relativity, because time actually runs at different rates out in space than it does here on Earth. All of those things are extremely complex, and we need to understand them better. And semantic spacetime is basically my attempt to formalize some of that and create tools for dealing with it.
Mm. And data pipelines, do you think will play any role in
Absolutely,
you know, applying this formalization of space timing, like real?
A data pipeline is also a clock, right? Every time some data passes from one location to another, it's a tick of a clock. But how do we count? Do we count each packet, or do we count each batch? Or do we have to wait for, you know, 2 megabytes before we can say we're going to do the processing? And when that processing happens, that advances one counter. So that's a tick of one clock. And then the next, it passes on to the next thing, which aggregates from 200 different locations, the same amount of data. That's a tick of another clock in that data pipeline. But of course, in terms of the clock on the wall, the first thing took 2 hours, the second thing took 12 days, but it's only one tick of the process clock. Exactly as in supply chain deliveries, you know, you can create 2,000 transistors an hour, say, but you can only ship them one batch at a time once a week. So the fact that you can produce, you know, billions of small things very quickly doesn't help you if you can only deliver them once a week. So these notions of time rates, the rates at which certain processes in business, in data are taking place, these are of crucial importance. And again, it's data pipelines all the way down.
Related to this, you are the editor of an upcoming issues on semantics and analytics in data usage in cyber physical systems. Can you say a bit what this is, and, you know, like what contributions you expect if data pipelines are, you know, part of this scope of the
I was asked nicely. I was asked nicely if I would edit a volume of the Information Journal. It's an open access journal, and often I say no to these things because it's, you know, it's a lot of work, and not everyone has time to write for special editions. But this is a special edition, and I thought, okay, if I'm going to do it, I will try to make it a very, very special edition, and invite people to write, you know, to save up their interesting ideas and visions of the future in this space to write something more than just sort of an everyday quota publication that we might want to add to our list of publications for, you know, money that we get for our funding. You know, we're in these strange times where the process pipeline for research, of course, involves certain deliverables, which we have to spit out a certain number of publications, but often that leads to a lot of uninteresting publications. What I'm hoping is that we can get people to present their ideas, not just some incremental results, but to think a little bit in detail, and perhaps even, you know, find a competitor and work with them to come up with something crazy, something new, some new thinking. How can we move the needle from just you know, publishing a paper to thinking up an idea, a new idea?
So it's going to be more like ideas for you know, how this data and semantics, you know, can. So you are not looking for specifically incremental results with evaluations, and it's more like high-level kind of thoughts around these topics.
I will consider anything that's interesting. So if people have results and they're cool, then let's do it. But I am definitely more interested in something out of the ordinary, because we see these data, you know, there are too many publications in the world as it is. If we're going to do another one, then let's make it something more interesting. Yeah.
So that's a question to Nikolay. If you have anything in the pipeline about data pipelines that could be submitted to this special issue. And maybe you can, Nikolay, can also comment a bit on DataCloud as a project and kind of technologies you are developing there, and you know, like what kind of technical innovations you expect with regards to data pipelines, and what people will be able to get out of this work in the DataCloud project.
Yeah, thanks for that question. So DataCloud is essentially a project that is centered around data pipelines. So we try to explore the entire concept of data pipelines and build up let's say a toolkit and a knowledge base of you know, different approaches on how to deal with the life cycle of a pipeline, starting from its inception, or let's say you have some data that you gathered around. We talked about this discovering of data pipelines, which is to some extent solved in the area of business processes and workflows. But the way that we look at data pipelines, they're kind of a subset of this bigger domain of workflows, where you have this manual processes and collaborations, orchestrations, etc. And in data pipelines, it's more about the data. So how do you get from some dark data that you have gathered, event logs, things like that, that you get the data pipeline? And then it's about the next stage would be, you know, how do you specify a pipeline which you discover? Like, how do you describe it in a way that is sufficient but not too much? We have this, well, a long time ago was developed this BPMN standard, which is very, very expressive and very powerful. But in my opinion, it's a bit too much for describing a simple data pipeline, because it deals with every possible problem that can arise. So how do you specify these pipelines in a way that, again, coming back to the separation of concerns and empowering the different stakeholders, that it's accessible, that you as a stakeholder involved in the development of the pipeline can, let's say, include your knowledge, include your contribution inside of the pipeline itself. So that means separating the concerns of domain experts from the concerns of technical experts, and making sure that both can contribute to the same process. And then when it comes to kind of provisioning or scheduling the resources necessary, first, before you do anything, you need to kind of understand the pipeline a bit better. So how do you test or simulate a pipeline's deployment? When it comes to big data, that may involve a lot of resources at very large scale. And, you know, traditional, let's say, approaches where you have either this manual expert knowledge that is available to you, where someone would say, okay, this step would be this much, it would need this much scale, and this is how many resources I need for it. So that would be one approach to feed in simulator, or another approach is just run it once or twice and figure out, okay, this is how much it actually needs, which are great approaches for, you know, small scale pipelines, because then you have the ability to actually test the pipeline and, you know, expect reasonable results. But in big data, that's not really feasible. So the big, let's say, room for innovation there is how do you get the data that feeds into your simulator? And that's something that we're looking into in DataCloud. How do you, let's say, implement the pipeline itself in a way that is also kind of accessible to a wider set of stakeholders? That's another thing. So kind of removing this technological vendor lock-in aspects of specific technical spaces, specific processing models of these widely available frameworks, which of course would be some kind of cost on optimality, let's say, how optimally a pipeline runs, but you gain a lot of flexibility in terms of what type of things you can deploy. And that's something that we're looking into is container technology. So like, instead of using these ad hoc processing models, we use containers which can host many processing models, if not all, and then using them for defining data pipelines. And then in scheduling, when it comes to a lot of these, we have this continuum of resources. So we look at the resources in terms of a continuum. So these cloud, fog, edge resources that are involved in a data pipeline, we look at them as one continuum and we try to treat them as such. And then calculating over this wide array of resources is in itself a challenge that we're looking into. Then nowadays there's also the possibility for in terms of resource provisioning, to provision resources that are quote unquote untrusted. So that we're talking about resources that are outside of the cloud or outside of your own premise, but can be made use of for data processing. And one interesting thing we're working on is how to use blockchain technologies for the management of contracting, let's say, such resources in order to perform computation on them and ensuring, let's say, the security of the data that is transmitted from there, and that it won't be violated, again, based on container technologies and virtualization. And also we're looking into online, so once the pipeline is running, how do we adapt the pipeline while it's online, runtime provisioning of resources, essentially, like how do you make this across the computing continuum so that you, with minimal interruption and disruption to the pipeline. So these are just some of the things. Of course, I don't have time to describe to you all of the innovations that the project is looking at, but I'd say that much.
That's great. As we are getting closer to an end, I would like to ask you, both of you, what would you like to see when it comes to data pipelines, let's say in a 2 to 3 years time frame? So imagine you are 2-3 years from now on. What would you like to see, like out there? Is it more work on the conceptual aspects of data pipelines? Is it more like tools that you can deploy? What kind of tools?
I will try and go first. I think I would like to see, so the cloud has morphed into containers to a large extent. The rise of container-based processing is very important, with all the service meshes and technologies like Kubernetes around those things. That kind of platform has won the current round of technological standardization, shall we say. I would like to see a system based on Kubernetes and service meshes where people can share data across different deployments of Kubernetes in different locations in a simple way. So a kind of standard set of libraries that are configurable with just by data, without the need for software engineering to make the connections between them. Something like this 8th level of the OSI model for data semantics, but between entities which are Kubernetes deployments, if you like, or container-based workloads. I think that would take us a long way towards the next level of innovation in generalizing data processing.
Nikolay?
Yeah, that was exactly what I was going to say. So container-based approach, but I'll add to that. I would like to see much wider adoption of big data pipelines, because nowadays, what I think is one of the things that is I want us to be able to remove some of the barriers for entry for SMEs or enterprises that are not Google, Amazon, and these big names that would have the technical power and the technical know-how within the organization in order to set up a real big data pipeline, and essentially reducing this need for specific ad hoc technological space knowledge that is very difficult to find on the market, which is getting more and more competitive. And I don't think that, I think that that barrier should be reduced or removed from the adoption of big data pipelines.
That was a great discussion. I thank you very much for your thoughts around data pipelines. As we can see, the concept of data pipelines is still kind of very broad, and there are many aspects we can work on. DataCloud project will work on some of these aspects that we discussed today, and during the next couple of years we will have such type of discussions where we debate and discuss about data pipelines. So thank you very much, Mark and Nikolay. And since we are very close to Christmas and New Year, I take this opportunity to wish you a Merry Christmas and Happy New Year.
Thank you, and same to you guys.